On April 2, 2026, the sky over Greece turned red. Satellite imagery shows a massive Saharan dust plume moving from North Africa across the Mediterranean Sea toward Greece, turning the sky dark orange. Not from fire, not from smog, from desert sand, from Saharan dust lifted by storms over North Africa and carried more than 2,000 kilometers across the Mediterranean Sea by atmospheric winds. The Acropolis in Athens was photographed against an orange-red sky. Visibility dropped sharply, flights were disrupted, air quality warnings were issued, and then in a few days it passed. Most of the Greeks watching the red sky had no idea they were witnessing one of the most consequential and least understood atmospheric systems on Earth. The global dust belt, an invisible highway of mineral grit stretching from the Gobi Desert of Mongolia to the Mauritanian coast of West Africa, crossing every ocean, controlling weather patterns across every continent, feeding ecosystems that cannot survive without it, and delivering increasingly dangerous health consequences to populations who have no idea the dust came from a desert half a world away. Approximately 2 billion tons of mineral dust move through the Earth's atmosphere every single year. 2 billion tons. That is approximately 250 million fully loaded freight trucks worth of fine rock particles suspended in the air above the entire planet simultaneously. And a study published in the journal Science Advances 2 weeks ago confirmed something that previous research had suggested but never so comprehensively demonstrated. Dust storms are hidden drivers of extreme rainfall. They are systematically associated with significantly higher precipitation across most of the globe in the 7 days following a dust event. The dust is not just a passenger in the atmosphere, it is a driver of weather. Subscribe to Where on Earth and hit the bell. Now let us understand the geography of the global dust belt from its source. A world map shows the global dust belt stretching from Mongolia across Central Asia, the Middle East, and across North Africa to the Mauritanian Atlantic coast. The global dust belt is a geographic concept that describes the continuous band of arid and semi-arid terrain that stretches across the Eurasian continent from east to west. It begins in the Gobi Desert of Mongolia and China. The Gobi covers approximately 1.3 million square kilometers of northern China and southern Mongolia. Dust storms from the Gobi are a defining feature of East Asian weather. Spring dust events from the Gobi regularly reach Japan, South Korea, and the Pacific Ocean. Some Gobi dust particles have been detected as far away as the Hawaiian Islands, more than 8,000 kilometers from their source. West of the Gobi, the dust belt continues through the Taklimakan Desert of western China, then through the deserts of Central Asia, through the Thar Desert of India and Pakistan, through the Arabian Peninsula, through the Sahara Desert of North Africa, the world's largest hot desert and the world's largest single source of atmospheric dust, and finally to the Mauritanian coast of West Africa, where dust-laden air masses exit the belt and begin their Atlantic Ocean crossing. North Africa contributes approximately 50% of all atmospheric mineral dust on Earth. Asia, primarily the Gobi Taklimakan and Arabian deserts, contributes approximately 40%. The remaining 10% comes from smaller desert regions in Australia, the Americas, and southern Africa. The dust belt is not a single uniform source. Different deserts contribute dust at different seasons. Gobi dust events peak in spring when strong frontal weather systems develop over northern China. Saharan dust events peak in summer when the West African monsoon pushes storm systems along the southern Sahara edge. Together they maintain a near-continuous flux of mineral particles into the atmosphere throughout the year. Now let us understand how dust travels across oceans. A MODIS satellite image shows an enormous tan-colored Saharan dust plume stretching from the West African coast across the Atlantic toward the Caribbean. When desert dust is lifted into the atmosphere by strong winds, it enters the lower troposphere at altitudes of 1 to 5 kilometers. At these altitudes, the trade winds and other large-scale atmospheric circulation patterns carry the dust great distances. The North African dust that crosses the Atlantic follows the northeast trade winds westward at tropical latitudes, the same winds that carried Columbus's ships to the Americas. A typical transatlantic dust journey from West Africa to the Caribbean takes approximately 5 to 7 days. During those 5 to 7 days, the dust particles are coated with chemicals as they pass through the marine boundary layer. They absorb water, they become coated with sea salt, they interact with ozone, nitrogen dioxide, and other atmospheric chemicals. By the time Saharan dust arrives in the Caribbean, it is chemically different from when it left Africa. It carries not just the mineral particles from the desert, but a complex mixture of chemical compounds acquired during its oceanic transit. And in summer 2020, an extraordinary quantity of this chemically complex dust arrived in the Western Hemisphere. Meteorologists and health officials nicknamed it the Godzilla dust event. a plume of Saharan dust so dense and extensive it was described as the most powerful Saharan dust storm to reach the Americas in approximately 50 years. The plume covered an area of approximately 8,000 kilometers across the Atlantic and Caribbean. In Puerto Rico, peak daily average PM10 dust concentration surpassed 450 micrograms per cubic meter. The European Union daily safety limit for PM10 is 50 micrograms per cubic meter. Puerto Rico received 9 times the EU safety limit for 15 consecutive days. Hospitals across the Caribbean reported significant increases in respiratory complaints. Asthma attacks surged. Elderly and vulnerable populations were warned to stay indoors. The Godzilla event was extreme, but it was not without precedent, and the trend is toward more events, not fewer. The United States recorded 20 sand and dust storm events in 2000. By 2022, that number had risen to 238, a 12-fold increase in 22 years. Now let us understand how dust controls rainfall. A cloud formation diagram shows mineral dust particles acting as cloud condensation nuclei around which water droplets form to create clouds. Water vapor in the atmosphere needs a surface to condense onto to form a droplet. In completely clean air, water vapor condenses only at very high supersaturation levels. But in the real atmosphere, tiny particles called aerosols provide surfaces for condensation to occur at much lower supersaturation. These particles are called cloud condensation nuclei. Mineral dust particles are among the most effective cloud condensation nuclei in the atmosphere. When a Saharan or Gobi dust plume moves into a moisture-rich air mass, it provides an enormous number of condensation nuclei. Water vapor condenses onto the dust particles, droplets form, clouds develop, and eventually, rain falls. The Science Advances study published 2 weeks ago analyzed global precipitation data from 1979 to 2023. It found that across most of the globe, precipitation in the 7 days following a major dust event significantly exceeds precipitation after dust-free conditions. Dust-laden storm systems have higher storm tops. They have broader upper-level precipitation areas with more large ice particles. They show stronger ice scattering signals and heavier surface rain rates than clean systems. The dust is not just associated with rain, it is actively making the rain more intense. This has profound implications for global weather geography. The monsoon rainfall of the Sahel region south of the Sahara is influenced by the dust lofted from the desert to the north. The Caribbean hurricane season is modified by the amount of Saharan dust crossing the Atlantic. High dust years tend to suppress Atlantic hurricane formation because dust inhibits the warm ocean surface temperatures that power hurricanes. The rainfall patterns of the Indian subcontinent during monsoon season are influenced by dust from the Arabian Peninsula and Thar Desert. The weather geography of the tropics and subtropics cannot be understood without accounting for the role of dust in cloud formation. Now let us understand the health consequences. A doctor examines a patient in a hospital emergency room while outside the window a dust storm approaches a city. When dust particles smaller than 10 micrometers in diameter enter the human respiratory system, they penetrate beyond the filtering capacity of the nose and throat. These particles are called PM10. Dust particles smaller than 2.5 micrometers, called PM2. 5 penetrate even deeper into the lungs, reaching the alveoli where gas exchange occurs. At the alveolar level, PM2. 5 particles can cross into the bloodstream. Once in the bloodstream, they trigger systemic inflammation. They are associated with increased risk of cardiovascular disease, stroke, and heart attack. They are associated with increased severity of respiratory conditions including asthma and chronic obstructive pulmonary disease. They are associated with neurological effects as fine particles can cross the blood-brain barrier. A Lancet journal analysis found that exposure to ambient PM2, 5 including dust contributions, is responsible for approximately 4.2 million premature deaths per year globally. But the health impact of dust goes beyond particulate matter. Desert dust particles carry biological and chemical passengers. Fungi. The coccidioids fungus that causes valley fever, a serious lung disease, is carried from desert soils in the American Southwest and northern Mexico. Its range is expanding northward and eastward as desert conditions spread. Bacteria. Research documented in the journal Nature confirmed that living bacteria are transported across the Atlantic in Saharan dust plumes. Some of these bacteria are antibiotic-resistant strains, potentially spreading drug-resistant pathogens across the Atlantic Ocean without any human contact involved. Heavy metals. Desert soils contaminated by industrial activity, mining, and warfare carry lead, cadmium, arsenic, and other heavy metals in the dust particles. These heavy metals travel with the dust and are deposited in soil water and food chains thousands of kilometers from their source. Caribbean coral reefs have experienced significant damage associated with Saharan dust deposition. The dust delivers both nutrients and toxic compounds to reef ecosystems. Research documented significant coral die-offs following intense Saharan dust events in the Caribbean, linking dust to a syndrome that weakens coral immune systems, making them more susceptible to bleaching and disease. And microplastics. Recent research has found microplastic particles in atmospheric dust collected from the Pyrenean Mountains far from any immediate plastic source. They were carried there from distant urban areas in dust plumes. The same atmospheric transport that carries mineral dust also carries the plastic pollution of human industrial activity across international boundaries. Now let us understand the expansion of the dust belt. Desertification is expanding the geographic area from which dust can be lifted. A map shows the expanding desert fringe zones across North Africa, Central Asia, and the Middle East. The Sahel region south of the Sahara has been under severe pressure from population growth, overgrazing, and changing rainfall patterns for decades. When vegetation cover is removed from semi-arid land, the soil is exposed. Exposed dry soil is vulnerable to wind erosion. Wind erosion creates new dust source areas at the margins of existing deserts. The same process is occurring across Central Asia, where the drying of the Aral Sea exposed enormous salt flats that now contribute to regional dust storms. The former Aral Sea basin has become one of the most intensively studied new dust source regions on Earth. Lake Chad in Central Africa lost 90% of its surface area in 60 years. The exposed lakebed is now a dust source contributing to regional dust storms across the Sahel. We covered the disappearance of Lake Chad in our Geography of Heat video. The connection runs both ways. Climate change drives desertification. Desertification expands dust source areas. More dust intensifies rainfall variability and heat retention in some regions while suppressing it in others. The intensified weather from more dust leads to more erosion and more desertification. Another feedback loop, like the permafrost feedback loop, like the ice albedo feedback loop, self-reinforcing, difficult to reverse. The U.S. Department of State has begun raising transboundary air pollution from dust as a diplomatic issue, when Gobi dust causes dangerous air quality in Seoul, and Tokyo, Korea, and Japan are not responsible for the Chinese and Mongolian land management practices that influence dust generation. When Saharan dust causes air quality crises in southern Europe, Europeans have no control over the North African desert conditions generating it. International frameworks for managing transboundary dust pollution are extremely limited. The UN Convention to Combat Desertification has 197 signatories, but binding obligations to reduce dust generation at source are almost non-existent. The global dust belt is one of the most powerful and least governed geographic systems on Earth, covering half the world, affecting every continent, with no meaningful international management framework. The dust crossed the Atlantic and turned the Greek sky red on April 2, 2026. It delivered fine particles to Caribbean lungs during Godzilla in 2020. It fed the Amazon with phosphorus from an ancient dried lake in Chad. It seeded rainstorms with condensation nuclei over the Atlantic and Pacific. And it carried bacteria-heavy metals, fungi, and microplastics from source regions to populations with no defenses against what arrives on the wind. The global dust belt is the most consequential invisible geographic system on Earth. 7 billion tons of mineral grit in the air above us, right now. Subscribe to Where on Earth for weekly geography that reveals the forces moving through the air around you. Hit the bell and drop your thoughts in the comments below, because the world looks very different when you understand the invisible highway above your head.